right. So we'll continue with the third invited presentation, which will be given by Denolle. Unfortunately, she was planning to come here in person, but the immigration office disagreed, I guess, and threw a wrench in that. So she'll be giving her presentation remotely, and she would be available tomorrow afternoon, or our time, if I understand correctly, for like questions by Zoom, if any of you want to have a bit longer discussion with her about the results that she will show. So yeah, so I hope that Zoom will hold out, and Marine, please take it away.
Thank you so much, Celine, for inviting me. And I'm really excited about your project in general. This effort to bring all these students to study, environmental sensing and a living Earth is really awesome. Something we're trying to lead in the United States, but we're behind you on that front. If that's okay, Marco, could you turn on the camera? Because I actually like seeing faces. I apologize for being distant. And so today, what I was planning on telling you about is how in my group we're trying to turn this big data analysis. Thank you so much. Hi, everyone. I really like seeing faces for the reaction of like, I don't understand. So today what I'd like to show you a little bit of the paradigm on how we're trying to use big data analysis, but make it small so that we can really harness all the data available to understand and monitor the natural hazards and the environmental hazards that we can sense with our seismological research. A lot of this work has been funded by the NSF, the Packard Foundation, and a lot of the software development has been done in part by the eScience Institute with the Scientific Software Engineering Center. But a lot of grad students and postdocs have really fueled the science and the software development. Okay, cool. All right, so I'll jump straight in. I have some ideas for like what the big data seismology grand challenge might be. One thing might be that we want to understand whether or not the Earth structure varies through time, or is it stationary, as we all assume in at least in seismic hazard analysis. So what can 20 years, which is the time at which seismic network started recording continuously on seismometers instead of triggered data 20 years ago in like early 2000, what can 20 years of continuous data tell us about temporal changes in the Earth structure, but now at global scale and with high spatial resolution? What can we do to discover new science fundamental principles using machine learning or aided by machine learning, but really swifting through petabytes of seismic data? Can we discover new seismic phenomena that our expert eyes had missed? We can use these new data mining techniques, and really what kind of new scientific understanding gain can we have from looking at this new data? And last but not least is the idea of, can we harness this distributed acoustic sensing data to benefit, broadly speaking, geoscience? The petascale here is already happening today. It's not a cloud system, but if it were to be available on a big computing system, can we discover new phenomena beyond earthquake geosciences, geohazard, tsunami genesis, and oceanography? There's just a lot to explore there, broadly speaking, in the geosciences. And so to give you a bit of context, maybe when I started my PhD 15 years ago, I was studying like 10 to maybe 100 stations at most. This was the size of the seismic network. The time scales were studying minutes, maybe a day, and the data size was very small, megabytes or gigabytes. But then we quickly moved in 2010 maybe to studying arrays that were 500 station plus, and then we were tackling the terabyte scales. And then nowadays we're tackling the thousands of channels with distributed acoustic sensing, but we also have 20 years, 10 to 20 years time scale of seismic data. So we're really in the era of petabytes. So I see cloud computing as a way to provide elastic, flexible, scalable data processing capabilities. And this is really a rapid evolution, at least in the United States, of exploring what cyber infrastructure can enable this large-scale processing. In 2020, McCarthy et al. 2020 showed that they could upload all the IRIS archive on, they could pull data from the IRIS archive on a cloud platform and demonstrated that they could really rapidly process data on the cloud. In 2024, this is a time where people, individuals in Earthscope are migrating data to the cloud, and scientists like us are exploring what that capacity would be. And this year, they're supposed to have all of this archive available to us. And so this is a time where the researcher will no longer be storing data on their laptops or towers, but it will be processing everything on the cloud. And so part of my research group has been to transition from the pre-2020 era, where we would download large seismic archives and process locally, to the post-2024, where we should be processing on the cloud. What is the cloud? The cloud is a computer system that provides what we call virtual machines. Virtual machines are abstractions of hardware and basic OS system. So they you can basically construct virtually single machines for your own use case. It also pairs well with what we call object storage. It's another kind of storage system that scientists use, especially for big data processing. The virtual machine is this emulation, virtual abstraction of a computer, where we can tune the number of CPUs, the memory, if we use GPU or not, and the type of and the amount of storage. And we upload on that an image, an operating system, maybe some Python, some libraries, maybe some home directory. But this is an abstraction of your computing environment. It sits on a physical hardware, but you're abstracting everything from designing the specs of your machine to the codes that you want to use. And so in a way, we've dealt with that a little bit, because especially your community is really up to date on moving software, to GitHub and so on. What's a little bit trickier in this context in the cloud computing is the idea of storage. You may be familiar with block storage is. It's something that is on your laptop. It's really small memory from 4 to 500 gigs. It's very fast. It's the fastest one you get. And it's also very expensive to use. You're also familiar with file storage. This is the one where you store your data in this kind of hierarchical folder-like structure. It's very flexible. It can go up to hundreds of terabytes per drive, and it's very cheap to use. And then object storage is this other way of storing data. It's even cheaper than file storage, and it has infinite, basically, scalability for data queries I/O. And so the cloud uses that for their storage systems. The cloud providers, at least in the United States, are Amazon Web Services, AWS, for their storage called S3. It's called a bucket. Azure, with a big A, is the Microsoft competitor. And Google Cloud, as you see on the bottom, is a third main providers. AWS seems to be storing most of the data, and that's where a lot of the NASA data products are for those who want to study time series and geospatial analysis, especially for surface processes. NASA has stored over 20, 30 petabytes worth of data at the least on AWS. But there's also, the Southern Seismic Network is there, the Northern California Seismic Network is there, Protomo DAS data was there, and the Earthscope archive is actually already there. So it's not available, but there. So there's already, maybe a petabyte worth of seismic data. Azure tends to have more of this environmental sensing data, lots of NOAA data, Landsat, Sentinel. And then Earth Engine, which is the cloud, it's like a kind of cloud platform for environmental science, also has a lot of like surface water, Sentinel DEMs type of data, and they have 70 petabytes of geospatial data. So these are the main players, and Seismology has typically done a lot more with AWS than Azure. How do we access compute on these machines? We can use a single virtual machine, VM, and it's great for exploration and machine learning training. And often what we would do is log in through SSH onto a machine, a virtual machine there, or we may use a kind of Jupyter Hub for single type of instance or virtual machine. That would be a couple of CPUs. Another way to work at scale is to use many virtual machines so that a deployment at scale will be operating through using containerized software using Docker. Some people like to build their own clusters with Kubernetes. It's hard to do it yourself, but it's possible. And then you can also use batch services that are the equivalent of kind of like a Slurm job if you were to use an HPC, a scheduler for big jobs. Some may want to use an infrastructure as a service. There's a lot of jargon in that community, IaaS, which makes it easy to abstract all of the system to launch jobs. The advantage of that, it's really easy to log in. Somebody hosting a Jupyter Hub for you as an instance. It's really sugarcoating all of the back-end machinery behind a launching job at scale and the types of memory you want to use, the type of instances. And so in general, I find like sugarcoating actually prevents us from understanding how the computer works and actually leveraging this new infrastructure for large-scale computing. In my group, we've developed a new cloud-optimized storage system for distributed acoustic sensing. And we've used two types of data formats, ZAR, which was derived for NumPy arrays, and TileDB. These are file formats that are very well suited for storage because they are pre-chunked, distributed on different objects. And we can use this called, we can take note of that MinIO is a software that emulates a cloud storage on your own Linux machine. So we were able to play locally on a virtual cloud with our own homegrown Linux environments. And we tested on what would be the cloud storage for distributed acoustic sensing using this platform MinIO and these data formats. TileDB is going to be the new data formats for the Iris or Earthscope data services. So we were trying to see what would be the best option for distributed acoustic sensing. And we did a lot of experimentation on data chunking in the files, trying to read through time or read through space, and did that for these two data formats. What would be the optimal way for seismological use cases, such as kind of template matching or earthquake detection or ambient noise cross correlation? What would be the best strategy to organize these files? And in exploring that, we found this kind of balance between pre-cutting the data, small but long time, or fat, different kind of architecture for what would be optimal for us. There's always a trade-off. There's no one best solution for everybody. So if we want to have a lot of small chunks, then it's too slow to read. If you have a lot of big chunk, you have to care about memory. But overall, it really allowed for good data compression. So I would kind of refer to you on this work to a paper that came out called DASTOR, where we tried to analyze what's the best compromise for seismological use cases for the cloud. This was for DAS, for array data. We found the opposite was true for broadband seismology. So bear with me there. This is a plot that we are of showing runtime. This is typical for big scale computing. The runtime is how long it takes to compute. This was an exercise to write on an S3 bucket and testing different file formats for many times in a loop. This is for a code called NoSPI, where we're trying to do ambient noise seismology, this time using broadband sensors. So what's interesting there is you actually care about the single sensor and not just the array. And so you may care about doing long-term analysis on one sensor in the Alps or one sensor on the coast to look at microseism. And so there we actually care about very small segments because we care about that one station, but over a long time. And so to actually find optimal way of storing this data, you have to go through this exercise of how long does it take to save the file, read the file. And we found really orders of magnitude differences in the type of file you would use. We found the TileDB and, stuff that's something that the Earthscope is proposing to use and adopting is actually inefficient for us to do ambient noise seismology. And we tried the ZAR because that was the kind of cloud optimized format. And then we found that a simple NumPy-Y, counterintuitive, but NumPy-Y format was beating the read time by a factor of 100. And on the cloud, this is still fast, relatively speaking, but you pay for every minute of your computing. And so if we do a lot of IO, which means like outputting a lot of small files, like cross correlations, you may output billions of these cross correlations. And so each of these runtime is multiplied by 1 billion. And so rapidly you can see how costs will go up. If you care about one station, it may not be an expense, but if you care about the 60,000 stations for the 10 years of data, you can see how this really amplified. So this is why we're kind of trying to develop this infrastructure. So that's a little bit it for like the type of like cyber infrastructure computing we're trying to do. It's really just how to read the file, how to do the workflow, so then we can make things small, quick, and be cost efficient. So now I'm going to show you two types of applications. They are both orthogonal actually in the way we compute in computing in general. I'll talk about the events-based seismology, where we care about one earthquake and many stations. Maybe I'll talk then about the ambient noise seismology application, where we care about the arrays and the long-term monitoring. In earthquake building pipelines, you may have seen the rise of, there's a couple of approaches. In the United States, Stanford has led a lot of that machine learning developments for earthquake catalog building. There's a very cool paper from Weishan Zhu, 2023, where he was the first to really do a cloud native workflow for machine learning on for building earthquakes. And so these kinds of cartoons are supposed to represent the flow of the data and the software. So work with me here. They designed a way to stream the data from Iris archives, reading with UpSpy. They had this modular view of picking seismic waves using FaceNet and TensorFlow. And then they aggregated this information using Gamma, which is a phase association. And then they were able to seamlessly spit earthquake location using HypoDD and design a kind of alerts emailing system. All of that using Docker container software. So this cartoon actually represents a little bit where we're going to. They had made their own, Kubernetes to orchestrate all of that, because they worked with software engineers to do that. I do not recommend anyone to learn Kubernetes. It's kind of boring and it's really hard to learn. And so if you're paired with a software engineer, good to go. Somebody can do that for you. But as scientists, we care about finding earthquakes or non-earthquakes. And this is a really big learning curve to get to that level of design for the CAD computing. So we wanted to experiment what is supposed to be from the ground up. I worked with two graduate students, Zoe Cross on the top and Uni on the middle, with the data scientist Scott Henderson. And we worked with with Azure, because, I live next to Microsoft. So they give a lot of money for cloud credits. And we wanted to experiment what it is from the graduate student's perspective. You got maybe like a FaceNet picker, and you have maybe or an earthquake transformer, or maybe you have a template matching exercise that you want to do, but your grad student had to go up and do all this process yourself. So what Zoe designed, and with EU, is if I were a grad student and I have two pieces of software, this is how we would go about in learning how to go through the Azure system. It's similar to Amazon, but how to containerize code, how to call the codes from the cloud, and pulling the containers, orchestrating the pool, which is a batch in AWS, how to orchestrate computing, how to orchestrate storage. There was a lot of learning that happened with that, but we had a very interesting, design and a learning experience. And so they've designed all this parallelized processing for Azure, how to create the software, how to flow through the data, and distributed this all. We had this fun experiment also of seeing, like, is this actually cheap to run? And we looked at scaling. So CPUs is the number of processes, and compute time is kind of like the run time we had earlier in the earlier plot. And we compared the template matching versus the machine learning face picking. And you can see how the curve goes down, the dots are going down, because they're showing you how as you increase the number of CPUs, it's much faster to run. That's the point of parallelized processing. So this is for the CPU one, and the comparison on the bottom is if you use a GPU for the earthquake transformer. We didn't try for the template matching. But you can see it gets to be faster. On the right side, you see the cost of running 1 month of data for, I think it was like 15 stations, maybe it was 1 year and 15 stations to do all of these template matching or face picking. And if you look at here, you see a couple of dollars. And what I want you to look at is it's only a couple of dollars if you've made this very well framework and if it's all running. So if you've designed it well, this is something that is cheap to run. What you can also see is if you scale with the number of CPUs, we actually didn't gain that much more in time because we're basically doing an embarrassing parallel job. So we're just running over time. It's the same cost because we're using the same machines for less amount of time, but more machines. So what you can see is that it's actually a template matching for CPU only was cheaper to run. It's also a different answer. So it depends on what you ask. But really that embarrassing parallel is just saying you can wait and pay, or you can just be impatient and just scale and pay the same amount. Another thing we found is if you use a GPU instance, because we're using a machine learning workflow, it was actually a lot more expensive than using a CPU for this deployment mode. So for deploying ML, we found like just use the CPU, and that's a lot sufficient. So that was our lesson. GPUs are expensive, CUDA is big, and basically you're pulling a big container on the web. So you're spending the time of downloading this container on your instance. And so that was a big cost. So you may cache it locally, but that was a big cost at that time. And if you design a small job and minimize memory and minimize throughput and really think about it, it can be very cheap. So our proposed kind of cloud native workflow for cloud earthquake catalog building is similar to Azure, has the same kind of concept where maybe we have data that's stored somewhere on the cloud. This is a lot faster to download when it's on the cloud. They also have much better computers than the seismic networks. So for some reason, it's just much faster to just be there and download from there. And we think it's very convenient. If somebody else pays for it, don't pay for it. It's really expensive. So once data is on there, we recommend to do use services like Docker to use your containerized software, use batch or pull to do parallelized processing. And then this is the time where you may do something like template matching, detection of earthquakes, face picking, maybe even discriminations between earthquakes and non-earthquakes. And there you create this massive metadata of event time and stations. And so we recommend actually using databases. You upload everything on a database. And then once you have, because these jobs are single station, single day, you're just picking, for each day, each station, aggregate everything on a database, and then you can have your post-processing aggregation workflow, maybe for locating the earthquakes, associating, where you aggregate all of these data sets. I should say this is a work that Jannis Munchmeyer and my team is working on as well, because he's very good at this. But we're designing kind of this on AWS to see how we can do the earthquake catalog building at scale. Another application that your team might be even more interested in is this idea of time dependence in the Earth structure. So what I'm going to show you here is a workflow we designed on the cloud with Tim Clements, who was a grad student. And our science focus was to look at changes in the subsurface over time, maybe due to earthquakes, but mostly due to a subsurface that's changing due to groundwater, changes in the groundwater table. And so this time series I'm showing was constructed from data. Data is shown on the top, about 20 years worth of data on the station in Southern California. And you can see the coda of that correlation function. So the wiggles up and downs are just the amplitude of the coda waves. Given that I have watched some of the SPIN talks, I think you've been exposed to ambient seismology. And you can see seasonal changes over time. You can see it clearly in the coda. And we extracted below is the DV, changes in seismic velocity up and down over time. And the bottom axis showing you the cumulative rainfall in California. California is a very varied state with a very diverse climate, but it's really characterized by 7 to 10 years of continued drought and then 2 years of massive flood. And so they oscillate from this drought period where they have to extract groundwater to satisfy the agricultural demands, but also 2 years of massive flood and good skiing and all of that. So what you can see on this axis, 2005 was a big storm. 2 years of a big winter with a lots of rain that resets the change in seismic velocities and continued with weaker resets in 2016, 2017. Completely reset by 2022, 2023. I don't have the data for that. So Tim designed this on the cloud. Let me just remove this, excuse me. And he used the computing language Julia. And he used 20 years of data, 700 stations. We pulled all the data from the Northern California data set then. It's on the cloud now. So we actually spent a lot of money storing that data for a few months. And he designed this workflow for just working with single station measurement. So it was about 90 terabytes of data to start with. We used down-sample data. And if you just look at single sensor analysis where you're not trying to crosstalk and aggregate, he was able to run it in only 25 hours, so one day, using one instance. You know, it's 700 stations. It's a lot of data to read. They're not cross-talking. We're not pairing anything. So that's just it. That's just the data you work with. But we don't need the cloud anyway because we were just using one instance. So it's one computer. And so you can see that this is an example where we did use the cloud, but really it could have been done in one machine in one day, provided that all the data was well connected. So that was actually a good learning experience. It's really thinking about how to make it small when you can read 90 terabytes in less than a day with one machine. We are experimenting on the cloud, on distributed acoustic sensing. This is with graduate students, uni, current student. There we have a cable that goes from the Seattle campus for the UW to the other. There's different campuses for the UW. And it's out of our office. So we plug in when we can. We have about a year or so of data. This is kind of modest size. We have 2,000 channel, 100 hertz of data. It's very classic for urban DAS to do this. And so Yiwu is designing a workflow that could be cloud or not cloud, but the idea is to create an Earth image every day or maybe every hour, because it doesn't really matter. The data is saved in 1 minute time chunk. We could repeat this workflow every minute. It's a fun computing exercise. It's not a case where there's drastic changes every minute, but it's just the idea of the concept of doing time-lapse imaging. And so he designed a way to do a cloud-native workflow by converting the data to a ZAR. He designed a ZAR format. He designed a Python client so we can get data from our emulated cloud store using this kind of UbSpy-inspired clients. We can select subarrays in that. We can read the DAS data. If some of you have manipulated DAS data, it's ugly. It's really ugly, especially urban. There's a lot of instrumental noise, there's cars and all of that. It's not the ideal environmental data we look for. Anyway, that's one example of the urban DAS. And then he designs it so then we can compute it locally or on AWS. By storing all this data, he designed it so we can do ambient noise cross correlations and using the classic nonlinear amplitude destroying processing, but they're still pretty good. 1-bit normalization, spectrum whitening. We constructed 8 billion cross correlation operation. This was an estimate, of course. And we used the classic AWS workflow. I think this was only $15 to cross correlate for about a month of data, I think. We use 67 instances. So it's a pretty good cluster. but it was not that expensive. So I'm showing now is the cross correlation of this subsegment of the DAS array. You remember, maybe you've seen these two lagged cross correlation, right lag, positive causal, left lag, negative anti-causal. The dashed line is the moving virtual source if we select the virtual source and then cross correlate with everything else. And you can see that X cross here is the waves moving away from the virtual source in all directions, in the two forward and backward directions. There's a lot of common mode problems with the DAS array, unlike broadband seismometers that have their own individual issues. DAS has one issue for everybody. So coherent noise is just boosted in this really ugly way that fused broadbands, you never get to handle these issues. But for DAS, you get to deal with coherent instrumental noise. It's beautiful. But you see this nice cross that indicates a moving surface wave, classic 500 meters per second. I think it's, geotechnical layer, shallow sediments. It's still there because there was a glacier in the past. And you can see no data, blocks of data where there's no data. That's when the fiber gets into telephone poles, which there you don't see like a ground motion from like weak ground motion traveling in the earth. Although, if there's an earthquake, the poles resonate well, so they amplify ground motion, so they can actually act as a fun amplifier of waves. So you can actually see during earthquakes waves in the poles. Side notes. Showing you another example of large-scale computing of this kind of ambient noise workflow in Julia. This is work done by Kurama Okubo. This is a work that is extremely reproducible to the most extreme sense that I've seen. Kurama spent 5 years on this project. He was a postdoc and then moved away, and then we meet weekly to finish this work. He worked on a kind of a contained project of 13 station, 20 hertz, 20 years worth of data, about 2 terabytes to start from. He processed all of this to do interstation and single station processes, and using 500 cores on a big HPC center. He also reprocessed everything on a different machine to obtain the same results. And then he containerized everything to be well documented on GitHub. And the code testing on GitHub is performing cross-correlation to make sure that every single subroutines and functions reproduce the same DV time series. So GitHub is cross-correlating. It's really the extreme case for code reproducibility. So I just wanted to highlight that case. Okay, so in terms of ambient noise, so I wanted to show you more of the software we're developing that is supposedly more generic and useful for multiple exercise. So this is the code from Chen Jiang, who started that in 2019, where we did this on a very simple Python code to parallelize cross-correlation. We had designed it, so then we would pull data from the web, cross-correlate the data using simple FFT, cross-correlation, stacking, and then we wanted to do 2 applications: ambient noise monitoring and dispersion analysis for Earth imaging. And we had kind of like this workflow that was designed as, download data, and we had this very monolithic, big, long code that was actually more like Fortran style than Python. And we use MPI to parallelize. And then we had an XCore step, S1, again, parallelized using MPI for distributed over cores to do all the cross correlation. And then we have an aggregation step to do the stacking. For those who are Python savvy, this is not a Python code. There was no classes, non-modular at all. That's just the way we coded from migrating from a MATLAB or Fortran style to Python. And so in doing so, we had designed it with the idea of Iris was somewhere, we save in H5, we output in H5. So we are redesigning it to be cloud native. And it has the same cores, same functions for cross-correlation and whitening and all that. But we're designing it so that now the data flows through a cloud store. We are doing cross-correlating. We're doing a PMAP, so actually shared memory for processing. We interface with the S3 bucket. We containerize everything. And we've explored all of the data formats. Turns out that you can go from one to the next very simply. And this is if you actually have good software engineers, which is part of the funding for this work, is he was able to write classes, Python classes that will allow us to go from one kind of backend a store, data store, like an HPC file system or a cloud store seamlessly. So while it's look under the hood a little bit complicated for starting grad students, actually grad students are better than faculty now, but you know what I mean, like starting Python expert, we were able to go from one to the next seamlessly. This is an example of the job that we run on the for exercise on the cloud for the Southern California data set, where we run for 300 station, created about 50,000 station pair. It's pretty modest, but it took about less than, it's like half a day to run using 60 nodes or 60 instances. Each of the instances were small and cheap. So we tried to do this as affordable as possible. And, you can see like it took about maybe less than a day total to process everything. It output 2 terabytes of data. It's only 1 year to start, so I think it was about the same amount of data inputs to outputs. So you don't want to download that cross correlation because that's a lot of data to download. We design it so then you're always on the cloud and don't touch anything. The only thing you would do is pulling the plots and saving the local plot, which took 10 minutes to make because you have to pull 40,000 stations, and so it's a lot of memory to load. So this plot to make and to analyze costs about $300. But if you don't analyze, don't change the processing, if you're okay with the quality or low quality of the correlation function for your interpretation, for your science after that, whether or not you're looking at noise sources, whether or not you're interpreting them crudely as a Green's function, that's up to you as scientists to make the call. But then this is your tomography, this is your roadmap to tomography. In this case, the proposed workflow is slightly different. We actually output too much data to be on a database. So there we interface with a cloud store directly. Cross correlation is just heavy. There's no way around this. And we need to store a lot of intermediate data products. And so there's no solution, but having a good SSD or good storage system that allow you to write with many instances, just dump a lot of this cross correlation on a storage system that's going to be welcoming of these thousands of writes per second. And so we work with S3 for that. And then we re-aggregate all the data in when we do a kind of move out analysis or monitoring analysis, re-aggregate all the data using another kind of cloud computing, whatever code that you run on the cloud. And maybe you would store your data product, which is a dispersion curve, or in DV time series, you would then store it on a database. So just to compare earthquake seismology versus ambient noise seismology for this big scale infrastructure, they all use very small codes that we run on many small instances. All of these are like 4 gigs of RAM, maybe 4 CPUs at most. And they are different in design. One is for earthquake catalog, we output a lot of metadata. So detection time, station location, but that's about it. We start from petabytes, but we output maybe gigs. Ambient noise seismology, we start from petabytes, we output petabytes. It's ugly. And so for that, we use S3. For the earthquake business or non-earthquakes like surface events, landslides, storms, you output the data on a database, and then you can re-aggregate all of that using nice containerized code. And then all the thing you download is your PNG for your paper. What's nice about this is you can automate all of this. And so anything you can save to reproduce it is not the data product per se. It's that YML file that allow you to configure everything. We could store the data products, but I want to caution, so like, what's the point? Storing data is energy. energy is CO2. And so we can store data that's useful for our science, but recomputing this might take you a day. So computing wise, this actually might be a lot cheaper to compute than to store the data. And we always think that we have amazing science that's so impactful that we want to store because somebody's going to use our data product for sure. You know, we have a lot of things to explore. And so our data products are actually quite specific and may not be useful. So in what we're experimenting, we're recommending that you just save the configuration file and the version of your software, and that can be rerun if useful. And then you just store your CSV file with your dispersion curve or your PNG for your figure, but reproducibility is built in this workflow. We store everything on GitHub, even the YML files, or you can store it on a database, and everything is talking to GitHub or talking to the database, but everything is reproducible because we need to automate this. Otherwise, it would be boring to do like manual fine-tuning and cumbersome. So building in this cloud native workflow is science reproducibility, but is also this idea of the energy bill for storing data. And where you don't see that maybe locally at your home institution, if you store data in Texas, you're spending a lot of gas. If I store data in Washington State, I'm feeling more comfortable. It's more hydro plants. But the idea there is like, okay, do I want to store my data and make it available, or do I just want to store the YML file because the reproducibility makes it actually cost efficient? And the computing is designed for efficiency. Out over there, I'll keep going through this, but what this workflow is enabling us to do is a lot of earthquake analysis. This is an undergraduate research experience. So imagine being a license level researcher. All of this reproducible workflow can be brought to really early researchers. And there we're doing kind of machine learning aided workflow to detect earthquakes in Cascadia. We can monitor volcanoes using this analysis, and we can use analysis of seismic velocity changing. And Peter Marcus is in your area, monitoring Mount St. Helens for 20 years. Manuela Kopfli was also at ETH, is doing all of this kind of data mining to find precursory events in Mount St. Helens. For eruptions, we don't find anything. We tried everything. But all of these kind of data analysis workflow to sense the Earth is just seamlessly, everything is reproducible, and we can recompute everything. And this is the type of analysis that it enables. Monitoring the Earth as it changes over time in volcanoes. We're detecting landslides and earthquakes using distributed acoustic sensing in volcanoes like Mount Rainier. Lots of fun things. But all of the software and backend infrastructure are really speeding up the type of analysis we do for our students. So the future of geophysical kind of science, I see a lot of potential for looking through all of these terabytes and terabytes of seismic data. Geodesy is also coming online, so we're going to be able to do cool like crustal deformation paired with our rapid time series analysis. And Earthscope, which is the logo at the bottom, has all of these archives on the cloud. Distributed acoustic sensing also for this is the offshore cables. If these archives enable and store them, I think we're going to have this nice platform we can send the Earth for multiple environments, so volcanoes and earthquakes and debris flows and what you like, whatever you want. Time changes in the Earth subsurface using this this cloud computing. I wanted to show some caveats to this. We have a lot of DAS equipment. This is a prototype we have at in Alaska from Ethan Williams, our postdocs. We set up a lot of DAS and edge compute. Distributed acoustic sensing, we may be interested, is just too heavy to actually transmit data anywhere. So the cloud is not practical for that. So one caveat to what I showed there is when data can be streamed to the cloud, DAS is far from being ready for that. I'll show you an example where on the edge, so on our machine there, we have 10 megabytes per second throughputs. We're not transmitting data. We're doing all of our computing there. And we get, this is an example where we have it, it's been a year already collecting this data. And we send on the compute there daily reports for earthquake waveforms. Alaska has a lot of earthquakes. It's really fun. only get an email with a PDF of all of these plots. We don't do any of the processing ourselves really on sites because the data is too big. But things that we can do that leverage on this cool software that is developed, especially in Europe, on the SciBench platform or kind of ecosystem is just phenomenal in helping us speed up science. So this is an example showing you of results obtained last week from postdoc Shibenshi, run on that computer that's stored right there where the end of our cables are. And everything is deployed on that computer that we installed there. We leverage the infrastructure that many of you in Europe built. We combine SciBench software for building ensemble deep learning. We combine the new PyOcto that Yannis made, and all of that within a couple of days because it's so well made by this community to develop very nice software. And we were able to integrate broadband data and DAS on site. But this is something that really we just don't want to do locally. We cannot transmit the data, it's too much. And so we're doing this on the edge. So I have a lot to show because science and infrastructure, but kind of to conclude on what will enable science is we found that for big science, we would leverage cloud or the edge. We don't want to do long-term deployment storage, very expensive. It's expensive to do code development. There's no point. Everything can be done locally. But we found that a lot of the processing that we want, if we can design them with very small data, very small code, it can be very fast, scalable, and affordable, provided that this is well designed. And so I think that's going to enable a lot of science that you're interested in. And I think I will stop there. Thank you.